Alright, in this presentation we'll talk about how to visualize transformations in R2. There's some particularly simple ways to visualize things, and we're going to use an asymmetric F shape. So we're going to visualize the action of a transformation on an F shape. So let's do a simple example here. Most examples will be the way to go. So let's use the map that takes xy and gives you minus yx. And you'll recall from the previous presentation that this is the same as r 90 degrees, or if you prefer r pi over 2, a counterclockwise rotation around the origin, holding the origin fixed through 90 degrees. And so if we draw this as an F shape, let me draw the x and y axes first in green. So here's the x-axis, here's the y-axis, and the F shape, the standard F shape, is going to be drawn like this. And here's the origin, 0, 0. Here's the 0, 1. Here's 1, 1. Here's 1, 0. Here's 0, minus 1. Think of those being the four distinguished points on the F shape. And in particular, there's a copy of the standard unit vectors. So right here is the standard unit vector I. So I is 1, 0. Right here is the standard unit vector j. J is 0, 1. And you may recall from linear algebra that the action of a linear transformation is determined by the action on the standard basis vectors I and j. So what happens here is we look at the image. I'll draw it over here. Here's another copy of the xy plane with the xy axes. And we think of what does A do to this. A sends, remember it sends the origin to the origin. So the point 0, 0 at the origin is mapped still to 0, 0. And you can see it from the formula here. The point 1, 0 has x equals 1 and y equals 0. So it's mapped to 0, 1. That's the image of the point 1, 0. The point 0, 1, by this formula, is mapped to the point minus 1, 0. So that's here. And now this is we can now fill in the entire F shape based on these two things. So the F, here's the point minus 1, 1. Here's the point 1, 0. You can check that that works for the other points, but once you've got the two bars of the F, that immediately tells you the rest of the F fills out in the same pattern. So we can see that the linear transformation is defined here. Xy goes to minus yx, takes this F and maps it to this F here. So it gives a very convenient way to visualize how the operation works. So let's try another example. This example will be a shearing transformation. Think of xy gets mapped to x plus y, y. Okay, so here the mapping is linear, as we discussed last time. The original F sits here. So here's 0, 0, here's 1, 0, here's 0, 1, here's 1, 1, here's 0, minus 1. And I'll draw the axes on there. The x-axis was here, the y-axis was here, and here's our new x and our new y-axis. And let's think what happens here. So we know the origin goes to the origin. So the origin always stays fixed. Now, 1, 0 maps to just itself, 1, 0. So here is 1, 0 again. Because at 1, 0 we have x is 1 and y is 0, so it maps to 1, 0. 0, 1 maps to 1, 1. And now we can fill out the rest of the F shape. So here's the horizontal bar on the F shape here. Stayed the same. The vertical upper part of the F changed to this. The vertical lower part of the F just is to here. So this is minus 1, minus 1. And the top bar of the F goes rigidly, stays the same rigidly over here to 2, 1. And you can plug the values in to see that all 5 of those points are correct. But the point is, once you know the origin stays fixed, the unit vector I stays as the unit vector I, the unit vector j turns into this diagonal vector going from 0, 0 to 1, 1. That immediately tells you the shape of the rest of the F. You just fill it in the same way. So for another example, let's try a scaling transformation. So here I'll use the following notation for scaling transformations. If alpha and beta are scalars, then S alpha beta of xy is alpha x beta y. So we're scaling the x component by alpha and the y component of the point by beta. So let's try a particular example. Let's try S of 2, 1/2. What does it do to the standard F? So again, here's the standard F. Here's the origin 0, 0. Here's 1, 0. Here's 0, 1. 1, 1. 0, minus 1. And what does S 2, 1/2 do to this thing? Well, it takes the origin to the origin. It takes 1, 0 to 2, 0 because we're multiple alpha is 0, so it's going to be 2, 0. And it takes 0, 1 to 1/2. Well, 0, 1/2. So the F, so here's the image of the horizontal bar of the F going across here, drawn in dark. Here's the vertical bar, and the bottom half likewise shrinks like this. And then the top part looks like this. So the F has been stretched by a factor of 2 horizontally and shrunken by a factor of 1/2 vertically. Okay. A special case of a scaling transformation is even a reflection around one of the standard axes. So for another example of this, we could look at S minus 1, 1. This is actually a reflection across the y-axis. And the picture is something like the following. Here's the F in standard position. So again, here's the origin. Here's 1, 0. Here's 0, 1. 1, 1. And 0, minus 1. This gets mapped by this reflection, S minus 1, 1, to the F that faces the other way. So here's 0, 0, 0, 1, minus 1, 1, minus 1, 0, and and 0, minus 1. So this is our reflection across the y-axis. So reflections across either the x-axis or the y-axis can be handled by using these particular types of scaling transformations. Normally when one talks about scaling transformation, one really means alpha and beta positive, because otherwise, if they're negative, you're getting some kind of reflection as well. And finally, let's try an affine transformation. So here we'll use the following composition of a translation and a rotation. I'll let a of x equal t sub 2, 1, composed with r 90 degrees of x. So what does that mean? Of course, that means that a of x is r 90 degrees of x plus 2, 1. So the 2, 1 here, this is what I called before u. It's the translation amount. R 90 degrees x is mapping, is rotating 90 degrees. So in particular, a of, say, x0, x1 is equal to negative x1, x0 plus 2, 1, which is negative x1 plus 2, x0 plus 1, which looks a little complex, but we're just going to break it down in terms of the composition. So we start off with an f in standard position. So here's the origin. 1, 0, 0, 1, and the rest of the points are as usual. And now we're going to transform it. Let's think of doing this in stages. We first transform it by rotation amount. Right, so that's r 90 degrees. What does that do to the f? Let's put the axes in. That maps the f 90 degrees rotated counterclockwise around the origin. So the origin is fixed, and the overall f looks like there. Here's 0, 1, here's minus 1, 0. And that's the effect of just the rotation part. But we also have the translation part. So t sub 2, 1. And what it does is it just adds 2, 1 onto every point here. So now we've got, a little bit hard to fit in on the board, but here's the y-axis and the x-axis. And what happens is that it's just translated. So here's like 1, 2, 1. So the origin maps to 2, 1. Right? And the rest of the f keeps its size and shape to look like this. So this point becomes 1, 1, this point becomes 2, 2, and the rest of the points fill in as expected. 1, 2, and 3, 1. So then we can see that this overall mapping, the mapping A, takes the f in standard position and gives you the rotated and then translated f. So it provides a nice convenient way to think about the shapes of these things. So that's all for this presentation. The next presentation will talk about matrix representations of linear transformations. Thank you.